So we've been working on calorimetry calculations, looking at heat exchange when temperature is changing in a substance, or heat exchange when we're melting or freezing or boiling or condensing a substance. What we're doing now is a fun lab, but requires some prerequisite math for students to be able to qualify, to be able to eat the ice cream we're going to make. Ice cream is what we're doing the math for here, and ice cream is our example problem for students to show that they can actually do these kind of calorimetry calculations. What we're doing here is to see, for a sample of salt water at a very low temperature, is there enough capacity to absorb heat energy from the ice cream mix to completely freeze it. Okay, before we start solving the math for our ice cream problem, let's look at the theory underlying the problem. In an ice cream maker, a homemade ice cream maker, you've got an inner container and an outer container. The inner container contains the ice cream mix. The outer container contains ice, rock salt, water, and a mixture of salt and water. For our example, to simplify things, we're just going to say that we have just salt water solution in the outer container. In order to freeze the ice cream mix, it starts out as a liquid. And in order to freeze the ice cream mix, all the energy that is stored in the liquid ice cream mix has to be removed to a point, not all the energy, but enough energy has to be removed to freeze it. You've got to slow the molecules down so they stick together. So enough energy has to be removed from it, heat energy. We've got to take the heat energy in the ice cream mix and move it out into the salt water. So Q, which is our representation in our calculations for heat energy, has to be moved from the ice cream mix out, and it has to be moved to a degree sufficient to completely freeze it. So the salt water out here has to be able to take in and absorb that amount of energy. We often just think about it has to be cold enough. It's not just being cold enough, but enough capacity to absorb the energy. And so that's our problem here. Do you have, for the values you're given, do you have enough capacity in this salt water solution out here, enough capacity to absorb the energy from the ice cream mix to freeze it? Every student has been given a different set of data on which to do the calculations that are prerequisite to doing the ice cream lab. Students have to be able to successfully solve the problem mathematically and logically before they're going to be allowed to eat ice cream. So what I've done is to pull up just one example of the problem that you're going to be expected to solve, and every student has a different set of calculations to do, so don't try to copy somebody else's work and expect me to accept it. There's a different set of data for every student. Okay? Well, here's one set of data. Given the following information, determine whether 3,030 grams of saturated salt solution, which is a liquid, at its freezing temperature can freeze 1,030 grams sample of an ice cream mix, and it's also a liquid solution, if the initial temperature of the liquid ice cream is at its freezing temperature. So what we're doing here is you're freezing ice cream that's already at the freezing temperature, but it's starting out as a liquid. For the ice cream mix, what we're trying to do is simply freeze that. So if you're trying to just freeze something, you're not trying to change the temperature of something that's already in a solid, liquid, or gas phase. You're using the equation Q equals mass times change in enthalpy. Okay, in this case, that's heat of fusion. For the salt water solution, rather than complicating these calculations by including ice in a salt and water solution mix. I'm simplifying it mathematically by sticking with just simply a salt water solution that has been cooled down to its freezing temperature but not yet frozen, so that you can just simply calculate the changing temperature, the energy given away, the energy absorbed of the salt water solution as it warms up, but no higher than the freezing temperature of the ice cream mix. And the ice cream mix freezes at 10 degrees C. So since we're warming up the salt water solution, the equation we're working with is Q equals mass times the specific heat of the salt water solution times the change in temperature. So let's go back to our problem here and look at the values we have here, all right? So the ice cream mix freezes at 10 degrees C. So this, on the side over here to the right, the saturated salt water solution, it can't get any warmer than 10 degrees C, negative 10 degrees C, and that's supposed to be a negative 10 degrees C, even though negative is kind of on a different line here. Just make sure you recognize that's negative 10 degrees C. This salt water solution can't get any warmer than negative 10 degrees C and still freeze the ice cream mix. So the final temperature you want to calculate is the negative 10 degrees C. The starting temperature of the saturated salt water solution is negative 21 degrees C. And as long as there's enough energy let's back it up and say it this way. As long as the salt water solution can absorb enough energy, enough joules of heat energy, to completely freeze the ice cream mix, then you will have all the capacity needed to freeze the ice cream. So going back to what we're working with on paper then, in this particular problem, remember you're going to have a different set of values. I have a mass of ice cream mix of 1,030 grams. So the mass of ice cream mix is 1,030 grams. 1,030 grams. The mass of saturated salt water solution is 3,030 grams. The enthalpy of fusion of the ice cream mix, that's the delta H term, is 155 joules per gram. The heat capacity of the water, that's the C sub P term, is 3.98 joules per degree C per gram, or per gram per degree C. Doesn't really matter mathematically which one. What we need to figure out is the delta T term. Okay, now what we said was that the salt water solution is going to start at a negative 21 degrees C. So delta T is calculated as temperature final minus temperature initial. And the initial temperature is going to be negative 21 degrees C, and the final temperature can be no excuse me, no higher. That's the ceiling, we'll call it. No higher than negative 10 degrees C. So temperature final is negative 10.0 degrees C. The temperature initial, the starting temperature of the salt water solution mix, is negative 21.0 degrees C. And we're going to subtract that negative 21 degrees C from the negative 10 degrees C. That's like adding 21 degrees C to a negative 10 degrees C. Now you can probably figure out how to solve that, but let's just go ahead and put it in the calculator that way. Okay? I'm going to go to the change of sign button. Not a subtraction button, but a change of sign button. It's right down here on this calculator. This is the change of sign button. Some calculators have a plus/negative. They have different symbols that mean the change of sign. Well, the change of sign, then the 10.0 degrees, and then minus, and then parentheses, here's a parentheses button on this calculator, 8, change of sign, and then 21.0 degrees C. We hit enter, and we'll get 11 degrees. Now you can probably figure it out on paper just fine, but that just shows you can use your calculator to figure out exactly and be sure of exactly what the change of temperature or delta T term is. That's 11.0 degrees C. Now you have to know, you have to be smarter than your calculator. You have to know that there's digits in the tenths place over here, and so you can't just go with what's on the calculator here. Calculator just says 11, but it's not 11. It's 11.0 because there's no empty slots right here in this column, so there has to be a 0 here. So 3 significant digits in this answer. So we now know what the delta T term is. The delta T term here is 11.0 degrees C. So let's calculate the ice cream mix values. What we need is we need to be able to freeze this entire mass of ice cream mix. And all we're going to do is calculate this right here to find out how much energy has to be removed from this to freeze all the ice cream mix, okay? Now, when we're freezing, we're taking energy out. So delta H is going to be a negative term. This value is going to be negative. We're just going to put negative there because anytime you're taking energy away, the enthalpy or stored energy in the system is going down, okay? So we're going to take Q. So Q is equal to 1030 grams times a negative 155 joules per gram. So what I need to know is how many joules is that going to give me. So I'm going to use a calculator here. So 1030 times, and then I want to use a parentheses to keep the negative term there in the correct place. So here's our change of sign button again. 155, enter, and I get this great big large number, negative 159,650, and that's joules. Need to round off let's cancel out our things that we can cancel. The 2 grams cancel. We're left with joules. And I'll round it off to 3 digits. So we get a negative 159,650 joules. I've got to have 3 significant digits because there are 3 significant digits here, okay, and 3 significant digits here, really, because that 0 is not significant. That 0 to the right would be significant if there was a decimal place, and there's not. So there's 3 significant digits here, 3 significant digits here. I need 3 here. I'm going to underline the 6, 5, and 0. I'm going to move the decimal place to write the answer in scientific notation. Anytime you're getting rid of a digit in the ones place, you've got to write your answer in scientific notation. Move the decimal place 1, 2, 3, 4, 5 places to the left. So we round it off, have to use an arrow to show that, to a negative 1.60. That's because this 9 is rounded up to a 10 because of the 6 here. That 10 carries over to here to make that a 6, 1.60. 1.60. Decimal place is moved to the left 5 places. 1.60 times 10 to the 5th joules. So that's the energy that must be removed from the ice cream mix to freeze all of it. Let's see if that amount of energy is available in the salt water solution. So Q is equal to the mass here of the salt water solution, 3,030 grams, times the specific heat that's given for the salt water solution, 3.98 joules per degree C per gram, times the change in temperature, which is 11.0 degrees C. Put those over 1 to kind of keep things nice and neat. Grams cancel. Degrees C cancels. Go to the calculator. 3030 times 3.98 times 11.0, and we get this really large number. 132,653. And we've got joules left. We cancel everything but joules here. Need to round it off to 3 digits. So we're going to move our decimal place Well, first of all, we're going to round to 3 digits, so let's underline everything but the first 3. 1, 2, 3, underline here, move our decimal place to between the first and second significant digit. Anytime you're rounding off a digit in the ones place, you must use scientific notation. 1, 2, 3, 4, 5 places. So we get 1 point, going to have an arrow there to show I'm rounding off, 1.32, actually 1.33, because this 6 makes it 2 round up. Anything 5 or 6, 5 or above, makes the number next to it round up when you're rounding off. 1.33 times 10 to the 1, 2, 3, 4, 5, 5th joules. So here's the question now. Is there enough capacity to absorb energy? Let's put it up here. Enough capacity to absorb energy in the salt water solution to completely take up all this energy that must be lost by the ice cream mix. Okay? Well, the absolute value of this is much larger. This number has to be bigger than this number to absorb all that energy. Okay? The ice cream mix has to give away this amount of energy if it's going to freeze completely. The saltwater solution can, between -21 and -10 degrees C, can only absorb this amount of energy. That's not enough energy to completely freeze the ice cream mix. So, for this sample, in this situation, the ice cream mix will not freeze completely. Now your numbers may give you a result where you can freeze the ice cream mix. But in this case, there just isn't enough capacity to absorb the energy needed. This amount of energy has to be taken away from the ice cream to freeze it. This is all that's available over the temperature range of -21 to -10. So this amount of saltwater solution will not freeze this amount of ice cream mix.